Okay, so this problem number 15 is an equilibrium problem. Then we jump back to chapter 14 just a little bit, but that's just fine. Equilibrium is the time when their rates of the forward reaction are equal to the rates of the reverse reaction. So if you have A going to B, you also have B going to A at the same rate. And so if you wrote a rate law for this, rate would be equal to some constant K concentration of A, and that would be equal to the rate in the reverse directions, which would be equal to some constant K reactant of B. And then you could solve for that, and that would get you the equilibrium constant, which would be a combination of the rate in the forward direction and the rate in the reverse direction. But you don't have to do that on a test. You just need to know that the rates are equal. And that's when you reach equilibrium. All right, number 16 now says, which graph shows the correct relationship between concentration and time for a reaction that is first order? So you're going to need your equation sheet right here if you don't have it memorized, and the equation sheet for 0, first, and second order reactions and their equations, and then the graphs that give them a straight line with a positive or negative slope. And you can see in the 0th order reaction it's concentration versus time. First order is natural log of concentration versus time, and the second order is 1 over concentration versus time. And so it's asking for a first order, and so what we want is natural log of concentration versus time, giving us a reaction with a negative or a line with a negative slope right here. And then number 17, 10 grams of a radioactive substance are present initially, and 2 grams remain after 300 years of a radioactive decay process. So I've got that on another sheet right here, and so in this we'd use the first order integrated rate law right here. And so I wrote that down as natural log of the concentration equals negative KT plus the natural log of X original, or amount original. That's what this equation gives us, and since it tells us there's a first order process, because radioactivity is a first order process, we can now put the numbers in. So this is 2 years right here, or 2 grams after a certain 300 years, which is our time right here, and 10 grams was our original amount, and then we have to solve for K. And so solving for K right here, I have the work down here, ends up being 0.00536 years. That's the rate constant to the -1, of course. And then lastly, for the radioactive decay described above in the problem, what is the half-life? So the half-life equation for a first order process is described right here. Half-life equation is T1/2 is equal to natural log of 2 divided by K. So natural log of 2 divided by K right here. K is this 0.536, so T1/2 would end up being 129 years for a half-life. There's some chapter 14 math problems.